Okay, so this video is going to be about thin lenses. This is chapter 24, section 5. I'll do two videos, one over converging lenses, one over diverging lenses. We are skipping over sections 3 and 4. We used to do more time with the graphical methods, but because of the online homework, I don't think we're going to try and do that this time. After the mirror, lenses is probably the most familiar optical device. I mean, I wear lenses. Many of you have glasses and contacts. Everybody's played with a magnifying glass. There's lots of applications. They're in microscopes and telescopes. The simplest type of lens is what we call a thin lens, and that's where you have two spherical surfaces that are close enough together we don't worry about how far apart. In other words, we don't have a lens over here and a lens over here. We have the lenses right up there together, okay? That's called a thin lens. So we're going to start with a converging lens. Some people call these positive lenses. A converging lens is always thicker in the middle. They can look like this. That's what we think of them looking for. That's called a double convex. They can have it where one side is flat and the other side is curved. It doesn't matter which way we put it. Well, one side's flat. That's called a plano convex. I kind of think that's hyphenated. Or we can actually have it where both surfaces are curved, but it's still thicker in the middle, and that's called a meniscus. I hope I spelled that right. Okay. So that's the different types of names. Let's look at how they work. Converging lens will focus parallel rays of light. To one of its two focal points. Every lens has not one but two focal points. If I draw a lens like this, they don't have to have the same radius of curvature. One side can be curved a lot or flat, and the other side curved some. But we'll draw that vertical line there. And then here's our principal axis right to the middle, or our optic axis that we've had every other with all our mirrors. Now, a thin lens has only one focal length. So if this one has a focal length of 20, that means 20, well, let's make it bigger than that. Yeah, 20. That means I'm going to have a focal point here, and I'm going to have a focal point here. Even though one side's curved more than the other, when you have a thin lens, the focal points are located at the same distance from the center both ways. We don't have two different focal lengths, even though we do have two different radiuses of curvature. This one has a lot more curve than that side, but those will be the same. We'll call this one F1. This one's F2. In this case, that focal length I drew was 20 centimeters. It's not really important for what we're doing right now. That's Miss Kraft texting me. I'm going to text her back in a few minutes. If we draw them, what we see is parallel rays. So here's some rays coming in parallel. I think I've mentioned it, but a good source of parallel rays is just the sun. All of those rays, when they go through that lens, will refract so that they go right through this focal point. Obviously, if we had a ray that was actually on the axis, it would go through without being bent. That's why we call it a converging lens. It takes parallel rays and it converges them to a single point. Okay? If we look at one other possibility, this is completely reversible. If I had a bunch of light rays that originated here and they were going this way, all of the light rays that originate at a focal point will emerge parallel, and they would all emerge going out parallel because those light rays are completely reversible. Okay? Let's look at how an image gets formed. This is a little bit of a ray diagram. These are kind of cool. So there's our lens. And here's the principal axis right through the middle. Let's see. Let's put our focal point. And let's put an image here. An object rather. Okay, so there's an object. How does it go? How do we go about forming images? Well, we know any ray parallel will refract through the focal point. So let's bring a ray across the tip. There it is. It's an incoming ray. And it will refract like that. Not sure how big I need this picture, so I'll make it kind of big and we may have to add to it. I don't know. So that's one of the principal rays. It comes in parallel, it refracts through the second focal point. The other possibility is that I have a ray that comes through the focal point. If I have a point that goes through this focal point, but it also goes across the tip of that arrow, coming in like that, it will refract parallel. Rays from the focal point refract parallel. I don't know, I may or may not have quite enough room. I think I'll make it. Just extend this a little farther. and you can see how the image will form. There's where the tip would be. Notice it's upside down, and you can also tell that it's real. We know it's real because these two different light rays actually meet here. So this gives us a real but inverted image. Okay. That's one way that a converging lens can form an image. The nice thing is our equations for the size and the location are the exact same equations that we had just a minute ago when we looked at the convex and concave spherical mirror. Cap all my markers before they all go dry. Let's look at an example. Okay. We're going to have a thin lens. It has a focal length that is a positive 30 centimeters. We know it's positive, it's a converging lens, and we're going to put our object at 50 centimeters, and that's a positive 50. We want to find where the image is located. We can also find what the magnification would be. So 1 over 30 has to equal 1 over 50 plus 1 over s prime. I'm not going to go through the algebra, but you're capable of doing it. And when you get finished, you're going to find out that s prime is a positive 75 centimeters. Okay. If s prime is positive, it means the image is on the outgoing light. Well, for a lens, we usually think incoming over here, outgoing over here. So it's someplace over here. You'll notice that when we have a positive value for s prime, this is telling us we're going to get that real inverted image. The magnification, if we want to find the magnification, is negative s prime over s. So negative 75 centimeters, positive 50 centimeters. And our magnification is negative 1.5. So the object that's going to appear, the image of that object, the image is going to be 1.5 times as tall. The negative is telling us it's going to be upside down. Okay. Converging lenses can make both virtual and real images. If we want to get a virtual image, we have to change things a little bit. Let's do an example where, do I have an example? No. Let's do an example where the object is not outside of the focal point, but inside the focal point. What if instead of being located at 50 centimeters, we let it be located at 15 centimeters? Well, if I do the math now and I solve for s prime, I'm going to have to do 1/30 minus 1/15. Grab a calculator. (1/30) minus 1/15. That's really going to be a negative 1/30, but I have to take the inverse. And I get that s prime comes out to be negative 30 centimeters. Let me show you what that would look like if I just sketch it. Here's this, here's this. The focal length is at 30 centimeters. The image the object rather, is right here. And what happens is it forms an object. Negative is going to be not on the side of outgoing light, but actually over here. It's going to form an image back here, like that. That's in fact how you can use, how magnifying glasses work. You can hold the, if you're over here looking at it, the object's really here, but it will form an image of the object right there that's actually quite enlarged, okay? In this case, the magnification, if I wanted to do, would actually be the negative of negative 30 over 15, so 2.0. Okay, I think that's everything that you need to know about converging lenses. Really important is that you understand that a converging lens has a positive focal length, that if you have parallel rays, a converging lens will focus those parallel rays, okay? One of the more common uses of that type of lens is, in fact, a magnifying glass, okay? The next video, we're going to talk about diverging thin lenses.